Okay, as I start, you probably heard that Steve Moises, an old friend of mine, had a family emergency, and so he has provided me with his slides that I'm supplementing a bit. Steve and I actually have close relationships on origins of life. I do work on origins of life, but I'm an organic chemist, and so it's a different perspective about, so we're both East European descent, and we both have this interest in origins of life. But I look at it a little bit like two chefs that you have, you give an egg to, and you say, well, can you make something out of it? Steve is like the French chef that would make the omelet, and I am like making the hard-boiled egg. So you get the hard-boiled egg version of this talk. So I have his slides. I've supplemented them a bit. I said I'm a chemist, and you see I have a tie that's a periodic chart I wear periodically. And here... So in his talk, hello. His talk was basically based on about what the Earth probably was. So this is origins of life and what were the conditions on the early Earth that allowed for the for life to exist, and what was not likely, what was likely in the earliest of times. And so Steve is very controversial, and he wants you to reflect that the state of knowledge, and you've heard some of the things already today, the state of knowledge that we have about the origin of life is changing, and people's ideas have changed over time. And what kind of Earth crusts were there, what kind of gases were in the atmosphere were all things that we should be thinking about. And so what he does is he uses fundamental principles of physics and chemistry to talk about the conditions that may have existed on the prebiotic Earth. All right. So I'm sticking with the title and of the topic sessions. I'm going to introduce with a few slides of my own to give you a foundation for these. And you know, the conditions that were on the Earth for the existence of life, we don't know, but we can talk about that based on rocks. You've heard about meteorites today, and we'll come back to all of those. There are other things that as we dive into trying to understand the origins of life, we keep coming up with questions about even why do we have the chemistry that we see of life in the present sense? And there's something called homochirality, that there are molecules, and I'll come back to this, that exist when there are possibilities of multiple forms, but life on Earth is essentially this one form. And so I will come back to that. And we have existence of fossils. The fossils don't go back that far into the history of the Earth, as far as you heard today about the 4.5 billion years. Most of those fossils are in really old rocks. And we have some of them actually look like they have like cell structures. And could they be forming naturally from minerals? You know, and we have these questions about life forms, but they're not the origins of life. These are all well-developed structures by the time that we find them in the fossil record. In fact, my specialty is also using stable isotopes, and I'll talk with you about this a little bit, because stable isotopes are a fundamental tool. Their carbon in your bodies is about 99% carbon 12 and 1% carbon 13, and machines in my laboratory that I could explain to you that they're called mass spectrometers that measure that 99% out to about 7 decimal places. And so we can tell when something looks like life because of the abundances of carbon 12 to carbon 13. And living things, living substances change those abundances using enzymes. So that's kind of a secret for understanding the origin of life. What's the record? Is it chemical or is it fossil? And so we can talk about that. So the great minds have thought about the origin of life. You know, going back, Charles Darwin thought you had to have hot little ponds for the creation of the starting of life. You know, something back in here, this period, something in there. And he thought, well, you needed something like these warm ponds in order to get life started. And in fact, in the early 20s, there is a fellow by name Oparin who was his idea, and this is kind of the joke, that you had a primordial soup in order to get life started. And if you had those compounds in the soup, then life would see them and it would somehow get started. You've already heard today about Stanley Miller and Harold Urey. Harold Urey was kind of the father of American chemistry. geochemistry. And they had this device that they set up, and they cooked a mixture of gases that they thought was the early atmosphere for a lengthy periods of time, and then they condensed out into, I would call it brown glop. Okay, that's a good scientific term. And that brown glop, this is the starting materials of what they thought the atmosphere could have been like, but no oxygen, because this is the early Earth didn't have oxygen. And so, and how do you get some results? Well, they had this brown glop, and there it is. And they published, these papers in 1952 and 53 that they had traps that they contained amino acids from this boiling water, and they were using like lightning bolts going across and sparking them, and they created primitive molecules. This was kind of unheard of, that they had these primitive molecules that they were able to create in their experiments, and they were loaded with amino acids. Not the same numbers of amino acids you find in your body, but in fact, a lot of those amino acids are associated with the proteins. Curiously, there were also an absence of what we would call nucleotides. These are the molecules that make up the DNA and the RNA. So they could make amino acids using this in this primitive atmosphere. So is this the right conditions? The rock record does not appear to reflect such a strange, and we'll call it reducing atmosphere. The chemistry of the products don't really reflect life as we know it, because you are all L-amino acids for whatever reason. Bacteria use a little bit of D amino acids, and that's about it. So where do you look for origins? Well, these are the amino acids, and you're all this, but in the spark discharge experiments, they were equal abundances pretty much of the Ds and the Ls. So how do you explain that? If you're looking for origins of life, was this a good model for that? Do you go and look back into the warm springs, the Darwinian approach? Do you go and look for the hot little ponds on the Earth? Or do you actually go deeper within the Earth and go to the places where there is plate tectonics action and you have hydrothermal vents, and we've actually sampled. And actually, if you can see that in the turquoise sweatshirt is me, and going diving in one of these locations. So that's a possibility. Do we go outside the Earth? There's a very good topic now at NASA is to go and find extrasolar planets. And do they have water? That's the key. We look for the water. And and this doesn't have water, but there's an ocean. And is that going to be a location where we can find early life? Or we go to Mars. There's a lot of discussion about Mars as having had life, or possibly having had life, because if it had water at one time. And Mars is small compared to the Earth, and we're going to come back to that in Steve's talk. So that's one location. Or do you turn to meteorites? So we've been hearing about meteorites today. Meteorites have water. Thturns out these meteorites that are from Mars, okay, and I heard how it was pronounced, and I didn't actually remember. There's the SNCs. They were anomalous meteorites, and they look like Mars because of the Viking lander. There are gases inside those meteorites that make them look like Martian materials. Hap McSween, who directs the U.S. program in Mars, calls them Mars-like meteorites. We don't have pieces from Mars that were actual retrievals yet. So we can look for meteorites. Meteorites may deliver organic matter to the early Earth. They may deliver water. And so there was a meteorite, elephant moraine from Antarctica, ETA 84001, and they had these structures in them, these organized microstructures. Were they an indication of life? Or do we turn to comets? Comets come in, we see periodically, could they have been a delivery mechanism for water for the Earth? Or could they have actually delivered some sort of life forms to an early Earth to go into this primordial soup? There are, Comet Wild had just been analyzed, and it actually has organic matter in it. Amino acids were found in the tail of the Comet Wild. So we're still looking. This is Marvin the Martian. Okay. So this is going back to now I'm into Steve's talk, and those were my additions, whether to lay the foundation. And what he was looking at was, well, if we look at the physics and the chemistry, can we actually predict or actually estimate what the early Earth was like in the conditions that would be suitable for life? And so what was likely or what was not likely? Can we go back to some of these models and say, No, that's not the way it was. Okay, and some of it's controversial. Steve's a controversial, likes controversies. So in this, he actually gives you a table of some of these words, and you've been hearing things like Hayden, and oxygen fugacity you'll hear a lot. It's a model for how much oxygen, and you can estimate that it's like a partial pressure, how much oxygen was available for a certain reaction to happen. And you'll hear about closing temperatures and chemical partitioning among the different substances, the different minerals. I find it curious, actually. You've heard about zircons already. And zircons are, he says, a very useful mineral. Zircons, if you go back and find the original, there's a term in Persian. And I know we have one of our teachers, might be from England, but he's from Persia. The pronunciation is like zircon, zircon, but it had been abused and modified, so it actually became a word that was like these words like jargon. And I thought it actually is a funny use of zircon being the term that we use, and it actually has like the jargon terms that we use in geochemistry. So what do you need for life? What do you need? What are you looking for life? And one of the things that you actually need is organic materials. And there's lots of ways of producing organic materials, as you saw in the Miller-Urey reaction. And they don't always have to be from spark discharge, but there could be other places, like in the meteorites, you have organic materials. We need energy, and the energy can come from vents, the warmth, the heat of a venting system. And in fact, there are people that actually say meteorites, when they crash into the Earth, produce energy that could have been creation of organic materials. And another clear thing that is kind of a limit is that you have to have water. And our perspective is you have to have liquid water, which means that we are in a narrow window for the conditions that we identify life as being liquid water. And if it's too cold or if it's too hot, it's a little bit like an old story of the three bears. It has to be just right, and it has to be a liquid water in order for life. And so it's a common limitation. So when we look to outside the Earth for planets that might resemble those of the Earth, we look for liquid water. If it's too cold, if it's too hot, it has to have gases, an atmosphere, because we don't know of life without an atmosphere. And then the magical part that we really need is you have to have time. And time of consequence is, what is enough time? Is time going to be too short for life to have happened? And that's where we can say, well, do the conditions on the early Earth give us sufficient time for life to happen? Or is it going to be time where the life was extinguished? And can we modify these criteria for planets and as being cradles of life, including for the Earth? What is that criteria going to be? And is this sufficient? Are there other criteria? Going back to our state of knowledge for what the criteria is for life. So raw materials. Stanley Miller had put together a figure that Steve modified and said, well, we have these prebiotic soups, and you can have these reducing atmospheres, and there I put on the hydrothermal vents as being sources of organic materials that are in the early Earth. And one of the things that really comes into question here is if you have an ocean, and the oceans go back to the early times of the Earth, and could this soup that had been speculated on with organic material in it, was it really a soup? Is it, so we've got the old model of the Earth was that it was this molten idea that it was too hot, and how fast or how long did that last? There is the time component. But our modern view is that the Earth itself was much cooler and maybe could have had water survive on the surface for a much longer period of time back into the history of the Earth. And is that going to be what we have to reflect on? Well, in fact, so for his presentation, Steve was going to be aiming at two themes, and one is that the mantle actually had an oxidation and reduction state involved with it that could have involved water, and what did that have for the types of systems that would have existed on the Earth as a precondition for life getting started. The crust, do you need the crust? That's fundamental. If you have an Earth covered in water, then do you need the crust in order to help to allow for life to get started? And here's one of the players. It has to do with volume. If you think about the volume of the ocean and the amount of organic material that are delivered, it's pretty clear that the primordial soup, when you think about you having chicken noodle soup or something like that, it's a fairly concentrated mixture of compounds. And in fact, the Earth itself, if it had this ocean, probably it really wasn't a soup. It was far too dilute by any of the mixtures that would have been the Miller-Urey type of system, or it was just so dilute that it probably didn't have that. So what about the gases? When we look at the gases that Miller and Urey were using, their gases were really reducing. They were hydrogen, and they had carbon monoxide and ammonia. And were those gases in the atmosphere for the early Earth? And can we look at the rock record? And in all apparent, it's pretty apparent that those gases, that was far too reducing, that the gases coming out of the volcanoes and filling the atmosphere were far more oxidizing. Not oxygen, but far more oxidizing, carbon dioxide and molecular nitrogen. So we look at the atmospheres of Mars or Venus today. That was probably more reflective. And if you look at the gases that come out of the volcanoes on Mars, that probably was far more reducing from what we know. So let's take a step back and think about the Miller-Urey oxidation, the Miller-Urey reaction, this spark discharge. And we can use the chemistry of some of the rocks to actually suggest that reaction where they're producing this primordial glop was in fact probably not correct. It was far too reducing, and what we can do is come back to that, and that the reactions that they had that proceeded, they produced organic materials. The organic materials were created abiotically. This is kind of good, but at the same time, did it reflect what we needed as a condition for the prebiotic Earth? And the answer is probably not. What Moises put together is this idea that there is something that he called the oxygen barometer, and using cerium as a indicator, looking at these materials that you've heard about already, these zircons, you can determine the ages of those zircons using lead and uranium. And if you compare that, this is one of the buffers for the oxygen, so this oxygen fugacity, that for the most part, all of those zircons that go back to the earliest time on the Earth actually fall in this region. It says that at the time of the formation of those zircons, the Earth had a fairly strong oxidizing potential. It had a fugacity for oxygen that was falling into this range that had to be considered. And in fact, he's expanded that with his own students going on. And so here's more recent things from him and others. And it says that, pretty commonly from the present, closer, younger ages, all the way back to the oldest zircons, the oxygen fugacity of the Earth didn't seem to change very much. And so that says we have this constant. Well, something about the Earth has made it so that, whatever we're going to be looking at as a condition for this system for the prebiotic Earth has to fit that model for these zircons. Added to that, though, with the acquisition of lunar soils, that you can go into the lunar soils and you can actually pull out zircons. And look at all those zircons fall far below that oxygen fugacity that determines, the potential for the oxidation of the minerals or the organic materials. And so the moon doesn't have that. The moon's far more reducing. So the moon's doesn't have the same capacity, even though the zircons, if you look at them, are about the same age. Something was going on with the moon that doesn't allow you to consider that. And so why is that? If you look at it, that the moon doesn't have the same oxidizing capacity. So the moon is only like a really tiny fraction, maybe 1% of the size of the Earth. And so it just couldn't hold on to whatever that was that the Earth held on to as far as an oxidizing system. What about Mars? Okay, you can look at Mars and say, well, we're looking for life on Mars. What do we know about life on Mars? Well, if you look at these meteorites, and you heard today that there are about 15 meteorites. People call this the poor man's space program because we actually have samples that we believe are Mars, although Hap McSween calls it the Mars-like system. And you can go into those stones and pull out the zircons, okay? And something that you may be wondering, like, how do you determine the ages of these? This is called a Concordia diagram. And right in here, and it's based around uranium and lead isotope compositions on these very tiny grains. And I encourage you to look at, the next speaker has a beautiful picture of a zircon inside the O on an American dime. You can get a feeling how small they are. And the idea that you can use that for determining uranium and lead Concordia diagrams so you can come up with an age for the zircons isolated from these Mars-like systems, these Mars meteorites. And you can then figure out, well, how do they fit with not only the age, but also for the oxidation, the oxygen fugacity for these ancient materials derived likely from Mars. And there they are. And so you've got Mars materials. They're all under this too reducing environment. They don't fit with whatever you see on Earth. And how is that for Mars that these also don't fit? And what it says is that if you look at the potential for gases in the Mars atmosphere, that the gases that probably come out of the volcanoes are more like the Miller-Urey reaction. They have methane, they would have hydrogen, whereas for the Earth, you have gases that come out of volcanoes that are far more oxidizing. So we have different environments on where life may have gotten started. So the oldest zircons on Earth, 4.4. Oldest Martians, 4.4. There's this convergence. The oldest lunar zircons, 4.4. All about the same age, but for some reason, they have different capacities for oxidation and reduction. Okay, so there's the Concordia diagram again. So what you have on Earth is an oxidizing environment. You have not as strong, it's not as strongly reducing. So if you're looking for an origin of life and how life might have gotten started, you have to turn to something that's a fairly recent, a good model, is something called the RNA world. So you have to have a molecule like RNA that came into effect very early and didn't really reflect life, but was the next step in the conditions for life. And RNA world, it meant that you had a molecule that had catalytic capabilities. It could act as a template for creating itself over. It could have evolution, it could have mistakes, and it could also be the model that you would have for an early Earth. It also gave the stability because of the oxidizing conditions of the Earth. It also said that molecules, not like amino acids, but like sugars, are going to be more stable. That's a fundamental molecule in RNA. You have sugars. And eventually, you didn't need the very reducing environments. You can have an oxidizing environment where organic materials could survive, and it could be a condition for life. RNA still exists in the Earth, in life today. Well, but there are problems with RNA. It breaks down, it doesn't survive heat very well, and it breaks down in the presence of some metals, and it's catalyzed very well. Although, the experiments that we have is limited to not a lot of work. And so that has the same problem with all the sugars, and there have to be some selective sugars. That's another question. On Earth, why do we prefer what are called the D sugars over the L sugars? That's a precondition for life. It's like the L amino acids being preferred over the D amino acids. And so this, if it existed, it was a short-term phenomenon and eventually gave rise to the molecule that we know and love as life, and that's DNA. and that's much more stable, and it's stable in the presence of all these ions. Well, those are going to be the saltwater systems, and the proteins can be made associated with DNA. So you have, today we have a selected number of about 20 amino acids that make up essentially all the proteins on the Earth. You know, there are lots of, in meteorites, we've identified about 70 different amino acids. Why didn't they take over on the Earth? But it's about 20, and they're all L amino acids. The RNA world hypothesis was a temporary phase in the conditions for the origins of life. So, as far as soup, you know, prebiotic soup on Earth was always a fantastically dilute solution. The joke he has put in here, it says, yes, you're right, it was dishwater, you know, so it's not really a real good soup. So how about the system of water on the Earth? And you have a lot of water on the Earth that's usually unaccounted for. We have lots of scenarios about where the water, did it come from outgassing of the Earth? Did it come from comets? Did it come from other embryos of planets hitting the Earth? In fact, recently there was a large snowball models that were hitting the Earth. And all of those were sources of water. But if you go through and do the calculation, in the mantle of the Earth, there is sufficient water for producing up to 11 times the volume of the oceans. The Earth is very rich in water, and it's all inside of these the rocks that are going into the Earth. And you can do this calculation about how much water is being stored in the Earth. Well, this is going to help control the fugacity, the oxygen fugacity, because it's in the mantle, and it's producing all, and potentially has all this water. There's a model called the Great Tack that Jupiter moved around in its orbit, and it caused a lot more water potential to be there. But just the very fact is that some of these carbonaceous chondrites we look at have a significant amount of water, and so they would be the source of water for the Earth. You don't really need to have other sources outside of the Earth to act as a source of that water. What about comets? Okay, so Comet Wild I've mentioned already. And here are, you know, they're dirty snowballs. You've heard that. They have potentially some organic material in them, and those could be a source of water. Well, if you look at them and you look at what we know about comets and we know about the planets, that and also meteorites, that pretty much those comets, if they come from Oort clouds, they differ isotopically. They have a different nitrogen-15 abundance than what we find on the Earth. So you don't really need to have that go with the comets. They show variability in the amount of deuterium. This is the heavy side, the isotope of hydrogen. And for the most part, we have a very common signal for things that are from the Earth and the surrounding planets. You can look at oxygen isotopes inside of places like the moon and say, you know, if the moon came from this impact of a Mars-sized body and helped create the moon. And it turns out that if you look at the lunar oxygen isotopes, that you've heard about meteorites, and these are type CM and CI, that for the most part, the delivery of water after the moon formed would be not consequential. The oxygen isotopes on the moon, which originated from this impact, assumed to be coming from this impact, actually, there's very similar. You can't tell the difference between lunar oxygen and terrestrially based oxygen. And if there was a difference of materials coming from space to help create the sources of water on the Earth, it would be, you could tell it night and day because of the stable isotopes. So water, for the most part, the conclusion would be that water itself was delivered at the time of formation, not a source from the cometary bombardment, not a source from other meteorite bombardment. In fact, even the large clouds type structures that were thought to be hitting the Earth, those isotopically don't match anything that we find on the Earth. You know, water being this volatile element that we help to make this buffering capacity for the oxygen fugacity was from the original accretion of the Earth, and it was partly helping to control the potential for the changing of the mantle. And so what you need then is you have to have a mechanism for concentrating, not just delivering material to a water-covered Earth, but also to have it concentrated. That means you have to have crustal platforms. You have to have some sort of places that were not going to be the location for a dilute soup on the surface of the Earth. You can say, well, was the early Earth because of all this water? Was it a water planet? It's a good question. It says, then you have to turn and say, well, when did the Earth start to have not just a water planet, but something on the surface that allowed for the water itself to have the concentration so you can have more of the molecules that would be there? And so what do you have to go? And this is all Steve's. And those are sources of something that would create islands. And what Steve does in order to help understand this differentiation of the crust from the mantle is that he uses a couple of other isotopes, lutetium and hafnium, in order to evaluate when did the mantle and when did the crust start to separate. And it turns out that you can use this and look, because it's got a half-life of like 37 billion years. And you can actually come across and try to figure out and evaluate that the mantle and the crust actually started to differentiate really early. And so you had islands coming up to the surface, and this continental evolution happened early. And so coming up on the surface, you'd be looking for something that would allow for crustal, the presence of crusts. And the presence of crust, so here is using lead, and here's a temperature for the formations. And you can have the evolution of the mantle from the crust as being an early event. That means that you had a mechanism for separating the ocean into smaller ponds. And if you look at the present crustal abundances, here's today, and that means that what you'd have to have is just at least some start. And you're not talking about a large amount, that only maybe 5% of the present crust could be present, and that's about the size of Australia. So you can have an early crust of the Earth forming really early, perhaps even 50 million years into the Earth. And so you'd have a crustal abundance for making this location where you could have concentration into organic molecules and maybe for RNA presence. Something about the size of Australia. So it could be there. So the question is, was the Earth a water planet early on? The answer is, well, not really, because you could have places that the oceans were separated into ponds, and this is, you could have had 100 oceans, and they were affected, but you did have dry land. The dry land is the key. Separating the oceans into a dry land so that you can have the location for life to get started. So, nope, it's highly likely that an emergent land existed really a long time ago, even though we might think that with the ocean you don't have that. And so here are locations that you can have that, and in fact, one example that he says is you can go, there's an island in the middle of the Atlantic Ocean, and these are St. Peter and St. Paul. And these are actually emergent, 4,000 meters above the ocean floor. It's an island that is actually representative of mantle material, so even today. So this could have been more like what the early Earth actually was. So is his conclusion, I guess on time, his conclusion were that the first habitats for life could have been formed really early, not the, we'd say 4.5 billion as the age of the Earth. And this is, some of his statements here are pretty controversial, that was like 50 million years into the Earth. You probably had the conditions for life to get started. And so this points to a lot of other locations outside of the Earth that you might be looking for. You had to have oxidized mantles for conditions so that life as we know it on the Earth And you had that. You had because of water, so much water, you had those oxidizing conditions. Liquid water on the primordial Earth, hardly any of it was supplied by comets. Embryonic planetismals hitting the Earth and providing a lot of that water was going to be present. The magma, magma forming events were part of the formation of the biosphere. The planets formed, they were originally hot, but they were hot enough so that when they cooled and they allowed for liquid water, you could have hydrothermal alterations of the rocks, and similar to our hydrothermal events today. And that this equilibrium existed, and it still continues between the melting rock and the atmosphere, and that's this coupling of the oxidation and reduction potential. All right. So, and that's with thank you, and my apologies to Steve for probably not saying things that he would like. Here's my own slide. I think we're still looking, and that's his slide. So thank you very much.